Lesson 3, understanding derivative and linear approximations. So there's times when we're interested in finding, notice it says effect of small change. Because remember when we've done that derivative where we have the point A, and then A plus H, where H is a tiny distance away. You're trying to get them to be 1 point. So the example here, for example, how's the revenue at your local theater affected by a small change in the ticket price for a movie? We can explore an application of the tangent line to a function called the linear approximation. So we're going to work with linear approximation. In all honesty, I don't feel like it's a whole lot different from other stuff you've done. You've already seen that a curve lies very close to its tangent line near the point of tangency. If you zoom in repeatedly on the graph of f at a point, the function will appear to be linear. When you've zoomed into a sufficiently small neighborhood around the point of tangency, it would be difficult to distinguish the function from its tangent line. This property of differentiable functions is commonly referred to as local linearity. Okay, so the idea that the more I zoom in, I can make anything look like a straight line. If I zoom in enough on that calculator, it's just like you're just looking at a blip of a graph. It's going to look like a straight line if we zoom in close enough. And so if that's at that tangent point, you're not going to be able to tell the difference between the curve and the tangent line is what we're talking about there. Okay, some exploration. It says use a graphing utility to graph y equals sine x. They've already done that for us. Let's investigate the neighborhood around the origin. Use the zoom in feature of the calculator at the origin 4 times. And actually, maybe we should do that. I've forgotten how I... Yep, go for it.
Sorry, what?
You all right, Kelly?
I've zoomed out so far that it's just like a horizontal line because it's something I hadn't zoomed out for before.
And then there's the option of zooming out will make anything look like a straight line. So, okay, so we're going to use y equals sine x. And it helps if I change my screen here, doesn't it?
You only have to zoom in twice.
Okay, so there's my calculator, right? You guys have y equals sine x graphed. Use the zoom in feature of the calculator at the origin 4 times. So the idea here is if I zoom in, now remember when you hit zoom in, it doesn't zoom in until you hit enter an extra time. Because right now it's wanting to know, okay, what's the centering of where you want to zoom in. There I'm zoomed in. So it looks like a sine curve, right? Zoom in again. That was only twice, I agree.
Yeah.
I'm curious. Has anyone gone the 4th time?
I have. It's not much different.
Not much, I agree.
Yeah, it's just still a straight line.
No.
But what's weird is I'm looking at their graph. Why is their graph like slightly off center?
That's what I'm saying.
Because it's like -0.64 and then 0.61. But when you say like zoom in 4 times, it gets you to -0.039.
Okay. Well, what I will say is she does not usually use a TI-84. She uses I can't think of what it's called. But when you watch her videos and she does any demonstration, she does not use a TI-84 usually, because that throws me for a loop sometimes when I'm, like if I watch her video thinking, okay, how do I teach this? And then I'm like, okay, now I've got to figure out on my calculator, like I've got to transfer it all over. But is it a TI-89 or there's another name for it?
Is it like the one that Katie has, Katie Beck?
No, hers is that same calculator.
Oh.
Hers is an 84.
So there's not like different teachers for like different lessons. It's the same teacher like all year long.
It's the same person that wrote. This is just the person who wrote the notes.
Oh.
So Katie has the TI-84 like this.
Oh, okay.
It's just the same. It's just the same. It's just an
older
older version. It's the non-color version.
Yeah.
Okay, guys. So once you zoom in, We've just proved it, right? It looks like a straight line. Okay, now, can you estimate the slope of this portion of the sine curve by inspection of this window? In other words, if I do a tangent line at the origin, at 0, 0, what's the slope of that line going to be?
Whatever the slope of that is.
Okay, what's the slope of that look to be?
1.
It appears to be about 1, doesn't it?
Yeah.
Okay, I'm going to use M. I'm going to use the squiggly equal signs. I can't really draw today very well, but M is about 1, yes? Exactly, who knows, but that's what it appears to be. We can pretty much see the rise of a run there. What can you say about the slope of the tangent line at x equals 0 on the function y equals x?
It'd be approximately 1.
Yeah. Okay, so because this portion appears to be 1, then the slope of the tangent line is also going to be 1, right? Because your tangent line, basically take this graph right here, impose it onto there, and that's what your tangent line looks like through the center there. Okay, if you're trying to, and I'm going to erase this, but if you're trying to draw, that's what the tangent line through the origin looks like. Okay, it looks like it overlaps a lot there, but it doesn't. So let's see, in my notes I have written the slope of the tangent line at x equals 0 is 1 on the curve y equals sine x. So slope of tangent line is 1 at x equals 0 on y equals sine x. That's just putting it all into words. C is asking you for the equation of the tangent line.
Y equals 1.
I
X minus, yeah, y equals 1. At 1x.
Oh.
X minus
It's all the
Oh my
Yeah.
gosh. No.
If you try and actually, I think you guys are trying to hit where Doug's at in the end. Think it through. How do you get to where Doug is? It's a slope of 1, x minus 0 in parentheses, and plus 0. What is that?
Y equals 1. 1x.
I'm going to go for y equals x. Y equals 1x, fine. Y equals 1, not fine. Okay, so that's the idea that you zoom in, anything can be made to look like a straight line. This one technically only took 2 zooms, but you can keep zooming in, and anything will be a straight line if you get close enough. Okay. Our favorite part, sketching tangent lines. In each figure below, use a straight edge to draw a tangent line beyond the point of tangency in each direction. You guys can use straight edge. Again, I love that these rulers are clear because it does help you. It helps me at least. I'm going to freehand them because I can't use a ruler on the BenQ and it stinks, let me tell you.
This one broken.
Have you tried? Does it like just not work out?
Well, because even if I like anything I put against here, like it.
Even like it can it. Oh,
How?
that sucks. Get one of those that have like the bump in them.
Because like if I use like if I want to try and use this as a straight edge,
Oh my gosh! What?
giving me an eraser. So
That's so sad.
it will either
That's
write
so
on my
sad.
BenQ or it will erase my BenQ. Anything I use to touch the
I
BenQ.
wish they had like a ruler.
Because
feature
even
in
like
there.
so here's my pen. I can use the back end of my pen too.
Can't you use your finger too if you really wanted to?
Oh yeah, I do all the time. So okay, anyways, we're sidetracking.
Yes. Sorry.
Okay, use a straight edge to draw a tangent line beyond the point of tangency in each direction. And, okay, there's a lot that goes down with this from down below because it doesn't ask us to find slopes right here, does it? This just says, right, draw your tangent lines. Because I have slopes written on mine, but it doesn't ever tell me to do slopes, does it? Wonder why I did that. Okay. Who knows? Something.
It's just distributed.
I'm not part B. Oh, sorry.
Point B is the easy one here, yes?
Yes.
I'm going out of order, but what is the slope of the tangent line at point B?
0.
Okay. I know it doesn't ask that, but it doesn't hurt us to talk about it, right? Okay, I'm going to back up and do A. I don't know. That's horrible. You're A. Make it look better.
Which
You guys have any thoughts on the slope of A here?
It was very similar to
I'd say.
I was thinking like 8.
9. 9 over 2.
I think 4.
I say mine kind of looks like it's 9 over 2,
Yeah.
which is 4.5. The answer key has 5. I heard 6. Are we in this ballpark?
Yeah.
I mean, I'm,
About 4.
you know, if you're in that ballpark, are we good? Yeah. I'm just going to put the answer key answer. I know mine's not going to match up exactly, but I'm at 4.5. It's supposed to be 5. Close enough.
A 4 would be okay, right?
Yeah. I mean,
I got negative.
I did too. What? -2.
Yep.
Oh, I see.
yeah, I can't get what I want there, but what are you guys saying on C?
Negative
2.
That's what the answer key has. Because you can go up to left 1. Yeah.
2.
Okay. Now, this next one is actually the easiest if you ask me. What about tangent line at A?
0.
There isn't one. Because it's like.
No.
There is one.
It's
Well,
It's tracing the line.
it is. It's tracing the line. Okay. I mean, here's the deal. The tangent line here, because it's a straight line, is just tracing the line.
Absolutely.
Because tangent lines, we usually talk about them being on curves, not straight lines. So what is the slope of A?
-2.
It's just the same slope as that.
It better be -2.
Okay. I can go with -2. I was miscounting. Now, what about B?
0.
Oh, I was like, B. I was going for C already. So. That is 0.
Well, kind of.
What?
Okay. So, over here, B was 0, yes?
Yep.
And it was legitimately 0. You're at the top of a curve.
Oh.
Now, bottom of a curve, top of a curve, doesn't matter. This is not a curve. That is what we call a sharp point, a hard point, a cusp, a cusp. Okay, like a sharp point on a graph is also known as a cusp. And so what you end up with here is that our derivative does not exist at this point.
The one time I could have used the D&E.
And you didn't get it. Okay, now, so I'm going to write a few notes here. That is what we call a sharp point. Okay. When we talk about why the derivative doesn't exist and all of that, or why you can't draw the tangent line, well, first of all, it would be teetering. Like, you're drawing it through a point, but there's no curve to really support it,
Oh, like a
if that
T-tar
makes
type of
sense.
thing.
Yeah.
Yeah.
Okay, so one thing I can say is doesn't work as 0. Would be teetering. Another thing we can talk about, our limits. The limit from the left, the limit as x approaches 0 from the left, does not equal the limit as x approaches 0 from the right in terms of, I said that wrong. This is in terms of the derivative, so in terms of slopes. I just realized that probably doesn't make a whole lot of sense, but one of the things we'll talk about for something to be differentiable, the limit of the derivative from the left has to equal the right, and right there we got two different slopes there, don't we? Okay, so there is your D&E option for today. What about C?
2.
I'm assuming it's going to be 2 without even counting because it looks equivalent.
This is probably, that's an absolute value, right?
It is an absolute value of V.
So it'd be like perfect.
I'm kind of thinking.
At least assuming that's what it looks like, so. Okay.
With these, with the tangent lines, they'd be on top, right?
Yes.
Okay, that's what I did.
Yes. Okay, so
I'm trying to talk.
if we think in terms of A here, yes, to answer Sophie's question, tangent line is on top.
Yeah, man, that was good.
Where?
B. How did you get a slope of 2?
Go from the point of 4, you go from where it starts. You go from point 2 to point 0.
If I go rise 1, 2, 3, 4, 5, 6. 1, 2, 3.
Why do you have to go from B?
I have to pick 2 points on the line. I don't have to go from B, but I need 2 points on the line.
I didn't
That
go
makes
from
sense.
B, but
I mean, I could have gone right here. If I go here, 2, 1, 1, 2 over 1.
Okay, that makes more sense.
It's 2 points on the line. I just picked the 2 dots because they were the obvious ones. Okay, your tangent line for A should resemble what I drew, kind of, sort of. What slope did you guys come up with?
negative 1 2/3. What?
All right.
My answer key says negative 1/2. However, is negative 2/3 in the ballpark?
Yes.
It's negative.
1 2
It's only
Huh?
6.
I heard from you negative 1 2/3.
Well, she was saying 2/3.
I said
I was saying
2/3.
I think you guys, I
1/2.
think you heard a combination of
Well,
voices,
it's like,
maybe.
I don't think negative 1 2/3.
So answer key says negative 1/2. I'm not even looking to see how mine was drawn at this point. What about the slope at B?
D&E.
D and E, because again, it is a hard point, or I didn't write the word over there, cusp. Let me throw that word in so you have it.
It was like, I know that.
You guys like that word. I don't know why that word's so fun, but
It just sounds fun.
okay. What about the slope at C?
Or 2/3.
It'd be curious to see when you draw this tangent line if you actually get it to be 1 2/3 again, or if you get it to be 1/2 this time. The thing is, it's hard when the point isn't on an actual.
I know.
Yeah, right.
I had to go from a point all the way down here. I had to go from like 2 0 to all the way
Okay.
over there.
That's how
Okay, are we on D?
Actually.
Oh, we just have point A here, don't we?
Yeah.
Okay. So,
I feel like it was the middle, doesn't it?
Done
Wait, actually,
as in,
I love when Ben talks about stuff sometimes and we just hear it.
So is it 1?
No.
0?
1 over 0.
It's a slope,
D&E.
so wouldn't it be 0?
Or is it 0?
here's the deal. What's 0? 0 is your
Not me.
horizontal lines when it's 0 divided by something. When 0 is in the denominator, we think of our slope as undefined, or no slope were the words you used when you first learned slope. In terms of this, I'm going to use D and E.
The one day I don't say D&E for every answer.
I'm going to say cannot exist when tangent is vertical. And here, we're really learning some derivative rules here is what we're learning, so. Not how to take the derivative, but. Okay. Now, 3, if I recall, refers to some of the stuff up above. Well, we're going to use the stuff up above to support our answers. How's that? The position of the tangent line relative to the function it models depends on the concavity of the function at the point of tangency. Throughout this course, you'll be required to explain, justify, and defend your knowledge using proper terminology and precision. Use the graphs from example above, number 2 above, to complete the following statements. Now, concavity. Do we know concavity or no?
No,
Really? Because I don't.
because I don't either.
Well,
I know what
was
the word
concavity in
means.
physics?
I know what the
No?
word means. No.
Okay. So, okay, let me back up for a moment. Increasing versus decreasing. We know what that is, yes?
Yes.
Increasing is as you move right across something, it's going up. Whereas decreasing, as you move right, it is going down. Okay, so concave is, and this is without an official definition in front of me, think of the way something curves or bowls, so to speak. If a curve is concave up, like a right side parabola, it's concave up because it's curving in, so to speak. Whereas if you have an upside down parabola, it is concave down.
Or convex. Right?
That's not a calc word. Okay, we're using concave up or concave down. Okay, so when something curves in, okay, that you're looking at your concavity, whether it's curving in and facing up, or whether it's curving in and facing down. Okay, and one graph can change concavity throughout. For instance, a sine curve. The sine curve is going to have multiple concavities, right? So like here I've got a concave up section, yes? But then over here I have a concave down section. And this is stuff to come, but where your curve changes, so like right here, those are the points where your curve changes. So like right here, these pieces are, whoops, that was a horrible trace. Those are concave up. What are my other pieces?
Okay.
Those are concave down pieces. Okay. So, okay, a little bit about concavity, right? When the curve is concave up, so concave up is going to be something like this. The tangent line lies where?
Beneath.
Can you guys agree with that?
What do you mean?
The bowl is up, like this. Then the tangent line is going to be down here.
But we have none where the tangent line was below.
Yeah, that's
Right.
because like that one's. Well, I mean, it's not necessarily it's not a curve, but
Okay,
it's on the inside.
so let's go with the opposite idea here. Okay, so like Sophie on C. This is just slightly curved this way, right? So it's just slightly concave down. Notice where the tangent line is? It's above it. This one is slightly curved down as well. Tangent line is above it. This whole thing is concave down. Tangent lines are all above it. Okay? Now, flip this parabola upside down. Where are all the tangent lines going to be? Below it. So I'm going to fill this in and say below the curve. When the curve is concave down, the tangent line lies
Above.
above the curve. I'm struggling with this chart today. I'm not sure I agree with it. At a turning point / max min, the tangent is, not sure I like the idea of turning point there, but that's all right.
It's horizontal.
So think about a max min. Did we have some max mins?
No?
Okay. Right. A.
We had a
Yeah.
max, yes?
Mhm.
What was the tangent line at that max?
Horizontal.
That's B.
Like,
Horizontal tangent line. Example A is what I meant.
Oh,
Okay. On example A, point B, horizontal tangent line, and that is the max, yes? I talked a little bit about this on number 13 in homework, right? Same idea. So the question here is, at a min-max, the tangent is, what can we say about that tangent? It is 0, as in it has a slope of 0, right? Or, what do we know about that tangent? It is horizontal. I know, it's kind of a guessing game. What am I looking for? Sorry.
it should give us a word bank.
really? Yeah.
Yeah, if you gave you a word bank, you would have been able to fill that one in perfectly fine. I agree. Okay. At a point of inflection. Okay, I did not use that vocabulary, but I talked about it.
Is where they
Here.
sign on the dots.
These are points of inflection, where your graph changes from concave up to concave down or vice versa. Those are inflection points, points of inflection. Okay, she'll call them POIs in here. At a point of inflection, concavity changes. The tangent is what?
Non-existent.
And why do you say that?
Because it's going to be a vertical tangent.
Example D. We have concave up, and then we have concave down. Point A is an inflection point. And at that, we have, it is vertical. So what do I have here?
Undefined.
I have vertical in this blank.
Okay. We need a bank.
I know, sorry. Okay, now.
Is the next one undefined?
I put the tangent and then it says line.
Hold
does
on a
not
second.
exist.
The tangent does not exist.
The tangent line. I wrote
Yeah.
it. I wrote it.
I will say, okay, so vertical is here because we have this example right there, yes?
Yeah.
However, and this is what I was just studying in my notes, I have down here as or, and I have 0, but because if you have, say, the cubic curve, you're going to have a point in there. Well, no, that wouldn't be a good example because that would be 1. I don't have a good example there.
I wanted them to be called concavities because that kind of cracks me up.
Okay, we're just going to go with that.
Sorry. No.
You're going to concavity.
Okay, at a sharp corner or cusp, the tangent
Does not.
Does not exist. I made that.
at a point on a linear function, the tangent is it's the, if we go back to our V here, it's the same as the slope of the line, right? Okay, so yeah, when you say slope, I'm going with that. So I have written the same slope as the line. Okay,
One more page
Um,
to get through that.
2 more
We
pages.
have
Oh, 2 more pages?
Yeah.
okay.
It should be at that point.
Consider the radical function y equals the square root of x. Use the difference quotient to find the slope of the curve at x equals 9. Sorry. I'm looking at how I have this done in my notes, and I'm skimming ahead to see if we have to do it this way or if I go with whichever way you guys suggest. Okay. What are we doing here?
Limit as x approaches 9.
I think the difference quotient is officially the other one.
Which one?
This is
Oh,
just
perfect. That's what I'm doing.
I think that officially when they say difference quotient, I think you're supposed to be using the h approaches 0, 1.
Oh. No, it's easy to do.
Depends, but. Okay. What are we filling in here?
E of y equals square root of x plus h minus the square root of x over h.
Are you guys with Doug? Because remember, it's f of x plus h minus f of x all over h, correct? Now what?
Multiplied by square root of x plus h plus square root of x over square root of x plus h.
What they said?
Square root of x.
Okay. Right now, you plug in 0, we get 0 over 0. We know that's not going to work. We've got to make some magic happen. So when you have those two radicals being subtracted, multiply by the conjugate of that. So square root of x plus h plus square root of x over the same. Notice I'm going to write the word limit. Limit as h approaches 0. Okay, FOIL the top. Square root of x plus h times square root of x plus h.
X plus H.
Outsides and insides.
Cancel.
And last, minus square root of x times square root of x.
Minus
X.
All over
H times
H times quantity.
plus H quantity, sorry.
h times the rest of it. Notice I did express as I didn't multiply it out. I put h times the quantity with parentheses. I'm going to keep cleaning. Limit as h approaches 0 of
1 over square root of x plus h plus square root of x.
You guys okay with that? X minus x cancels.
Yeah.
And then you'll have an h and h that cancel, right?
Yeah.
So 1 over square root of x plus h plus square root of x.
Now we plug in our zero.
Plug in our 0 for h.
And then you just
1 over 2 square root of x.
Okay.
Over 3 square root of x over 2x.
I did just spell it.
I'm just going to do 1 over 2 square root of x. And I'm going to write this. In my notes, I have this written as f prime of x as 1 over 2 square root of x. I have it written as f prime of x because it is the derivative of f at x. Yes, you could rationalize, but unnecessary. Okay, we're going to leave it like this, 1 over 2 square root of x. What were we specifically asked to do in this problem?
Positive interval x equals 9.
We want to find it at 9, so now I'm going to do 1 over 2 square roots of 9, which is
1 over 6.
1 over 6. So what is that? That is
M of
f prime of 9. It is m. And it equals 1/6, right?
Yep.
Okay. B asks us to write the equation for the linear approximation of f near x equals 9.
Y equals,
y equals 3.
yeah, no, 3.
Okay. They use the phrase linear approximation, like you guys are starting to do. Yes, just think tangent line. So what was it?
Y equals 1/6 x minus 9 plus 3.
What's this plus 3 you talk about?
y equals square root of x, which would be y equals square root of 9.
Yeah.
You get plus.
In order to do this, we need a point, yes? We have the point x equals 9, but what's the other half of that? It's going to be the square root of 9, which is 3. We already had our slope. So I agree it is a plus 3 at the end. Are we good there?
Yeah.
Okay.
I hate C.
C.
Yeah, for my.
Oh, you don't like it because of the bold words, right?
Well, no, it's just like,
Maybe
why are
the
they
square root of
asking us
9.1.
this? Yeah, that's what it is.
But we're not doing the square root of 9.1.
Yeah, but
It says
looking
estimate.
at it, it's like I don't
We're using
know.
our formula here, though. Okay, so, use the equation in B to estimate the value for 9.1. Do not use a calculator, show your work. So basically, this was, remember the vocabulary? Yes, we basically wrote a tangent line, but it is a linear approximation. So any values close to 9 will have this, carry the value of this equation. So we're going to find, I'm writing it as f of 9.1. I probably, when I say f of 9.1, I'm meaning plug it in here, yes? It told us to use the equation from B. So 1/6 times 9.1 minus 9 plus 3. What do we know about 9.1 minus 9?
Equals 1/10.
So now I have, and I'm going to write it like I think a lot of you will do right now. I wrote it as 1/6 times 0.1 plus 3. Is that what you guys did? I'm guessing.
I'm just
Now.
1/10, but
What do we know about 1/10 as a decimal?
That's 1/10.
As a fraction, it is 1/10.
So you get 1/60th plus.
So could we easily multiply without a calculator 1/6 times 1/10?
yeah.
Yeah. So that is 1/60th plus 3, which is going to make this
181 over. Oh, 3 must be. I was gonna go 181.
I have 3 and 1/60th written down.
181 over 60.
I also have a decimal written down. How did I get that decimal? I had to have used a calculator. And I'm wondering if,
Well,
What- 1/6?
16.66666666.
No, 1/6 is
1/60th.
0.33.
Oh.
Wouldn't it just be
No, I was thinking, do like 1/6, you got the fraction of
0.06?
I'm using my calculator.
0.1666666, and then you times that by 0.1.
Oh, if I can get
Sounds like a lot.
3.06.
I see what you're saying there.
Oh yeah.
So I see where Doug's going with that. Again, I'd be happy with 3 and 1/60th. How do I have this written in my notes? I just have that. Okay. Again, not the big concern here.
Would 181 over 60 be?
That's equivalent to.
Okay.
But I left it more as 3 and 1/60th only because this should be close to 3, right? And that's what I'm trying to show. Because square root of 9 is 3, so square root of 9.1 should be something close to 3, just a smidge bigger. Okay, D. Graph the function and its tangent line at x equals 9. Okay, guys, when we talk about graphing the function, y equals square root of x. Starts at
0,
0,
0,
0, goes through,
1, 1, 2, 4, 3.
reverse those pairs.
What?
1, 1, not 2, 4,
4.2.
4, 2, 9,
9.3.
Oh,
3.
I see what you're saying.
You just were saying backwards. 16, 4, since they have the graph going over that far. Horrible place to stop. And its tangent line at x equals 9. So at x equals 9, its tangent line, which
That's hard to draw.
it is. Something like that.
Good enough for me.
Okay. Bell's gonna ring, so I'm gonna have to stop at that horrible place. We couldn't get through E, F, and G. Of course not. And we'll have to pick up there tomorrow.
We can go calculator.
Dad didn't watch.
Get it on.
It's dead.
Oh.
Didn't charge it.
Thank you.
What's that? My watch.
Okay, we'll pick up there.
You're probably too tired to.
Yeah.
Thanks, Dad.
Of course, now I actually had a few more minutes than what I thought, but oh well.